Hi, thank you for the introduction. My name is, I'm from the University of Chair of Information Centers, and today I'm glad to present my topic as the grid-friendly microgrid management with community hydrogen storage in the German electricity market. So that is kind of also flexibility energy storage related. So let's start with short motivation. So there was a report from Bloomberg. It says that the negative day-ahead price is now becoming the main concern, especially during holidays for Europe. And also there is a news in German, and one German expert also suggested us to switch off our PV system, especially during holidays. And it says that the German electricity system does not have a generation problem, but it has a flexibility problem, because there is a mismatch between the demand and the energy generation through the renewables during holidays, which results in the feeding peaks and can cause negative price like renewable retirement during holidays. So instead of just switching off our PV system, we need to find some additional flexibility options and to absorb these surplus. Until now, the mainstream storage system is the battery storage system because of its fast response, higher power efficiency, and it is also a major technology. But on the opposite side, it also needs high investment cost per kilowatt hour, and it is hard to scale. So when we talk about the traditional microgrid, each household will have a battery storage system to smooth the solar power fluctuation, right? And it is very good for the short-term installation, especially the day and night. But when we talk about the seasonal fluctuation of renewables, the battery is not able to store that amount of energy, and each household can hardly scale up their private battery because of cost. And sometimes the grid operator also needs something to deal with the electricity peak. So we think about the hydrogen storage, and the target of this presentation is the analysis of the shared hydrogen storage in the microgrid as a flexibility option. So we give the microgrid access to one shared hydrogen storage, and each household is then connected to this hydrogen tank, and grid operator may also use this hydrogen tank as a flexibility storage buffer. When we talk about the previous literature, we see that previously they talk about the PV system, the hydrogen storage, battery storage, like in the first three papers that I presented, but they not consider the shared hydrogen tank in one microgrid community because the control method they use are the rule-based method. The rule-based method means that if there is an excess in the PV energy, it will be first feed into the battery, and if the battery is full, it will be fed into the hydrogen, then afterwards it will be sold to the grid. But in the machine learning era, we now have the reinforcement learning method, so they are talking about kind of shared hydrogen option for different multi-agent households, but they barely consider all these parameters like PV, hydrogen, battery, and degradation, shared hydrogen tank at the same time. So in our idea, we want to close the existing research gap of investigating the feasibility of the overall community-based microgrid system. So in our framework, we have a grid connection, so we use the electricity price from the historical day-ahead price. And we have 4 different households in South Germany with different PV generation power, and the load profile is also collected from the South Germany, and we give each household 10 kilowatt hour of battery capacity, and we define a shared community hydrogen tank in this case. So in this setup, the household will have 3 ways to supply the load. So first, the household can use the solar power directly, so the solar power could be used for the load, for charging the battery, or charging the hydrogen tank. Second, the household can use the energy storage system to supply load. It can extract electricity from the storage system, or the electricity could be directly purchased from the grid. And the grid operator may also use the hydrogen tank as some additional grid storage option. And there is some traditional energy balance equation so that the energy flows meet the requirement of the equation. So there is no newly generated energy beside of these equations. And we define that there is no direct exchange between the grid and the storage system, so you cannot purchase the electricity from the grid and charge your system directly. And we also need the different behavior of each household, because each household has different interests. So we want to use the reinforcement learning to output the perfect action for each household. So we define a policy, and the policy outputs the actions. The action will consider the charging and discharging command of each household for the two storage systems. And we also establish a custom microgrid environment. So the goal of each household agent is that to minimize the cost. So the cost will include first, okay, the electricity cost. So the agent wants to minimize the electricity bill. And second, it wants to also minimize the battery utilization, because if the household wants to replace the battery, it will also increase the cost. And for the training procedure of the agent of the reinforcement learning, first we use the historical real data from the Germany electricity market, also from the Germany geographical data, and we feed the data into a global model predictive control to output the perfect information, to output the perfect action under the 1 year information. And we train our agent based on the behavior cloning and fine-tuning. So the agent will initialize from the perfect actions from the global MPC. So then we will have a policy for different households, each household afterwards. And if we talk about the result, we want to analyze the benefits of implementing a hydrogen tank in that microgrid. So we define two different cases as analyzed. So first one is the case operator. So we want to minimize the peak in the transformer. We want to minimize the peak in the community. And in this case, only the grid operator has access to the hydrogen tank. And the household still only have the battery storage system. And in the second case, we define that the household could also have access to the hydrogen tank, where they could use the hydrogen tank as a second storage option to reduce the total annual electricity cost. And if we look at the first case, where only the operator can access the hydrogen tank, we see the 4 different behaviors of the 4 households, and we also see the aggregated electricity at the transformer. So if we focus on these 3 plots, so that's the 2 different bidirectional behaviors from 2 households, and also 1 electricity power at the transformer. And we look at that, we will find that the household will try to sell the electricity to the grid, especially between May and October, and which results in a huge pressure in the grid transformer also between May and October. So if I am the grid operator, I want to reduce the load. I want to reduce the peak load for my transformer with the help of the hydrogen storage system. So I can store this excess PV energy generation into 1 hydrogen tank. And if we define 3 different scenarios, so we define different percentile of the max feeding power, so 90%, 70%, and 50%. And we see that if I'm a grid operator, I want to reduce the peak feeding by 50%, then in this case I need 2,800 kilowatt hour of a hydrogen storage system. And if I want to reduce by 30%, and it only needs 850 kilowatt hour, so the relation between the production and the capacity of the hydrogen tank is non-linear. And if we look at the case households, so the household will still have access to our hydrogen tank. As a second storage option, the household could utilize the hydrogen storage to store these excess in the summertime. And we see that if there is no hydrogen tank in this microgrid, so the annual total grid feed-in will be over 1,100 kilowatt hour. But with a hydrogen tank, so the household could store some energy into the hydrogen tank. And there is a reduction of 42% in the total annual feed-in. And the needed hydrogen tank capacity is around 2,758 kilowatt hour compared to no tank sharing. So if the tank is not shared by the community, it will be 2% more. And if we look back at the behavior of one household, so in this case, the household used hydrogen as second storage option. So we see that the buy and sold to the grid is minimized compared to the previous situation. So in the previous situation, the household only used battery storage, so it will have more cell, like more electricity cell to the grid, especially in the summertime, and it will buy also from the grid in the winter. So if we look at the heat map, we will find that the AC shows different behavior for discharge and charging for battery and hydrogen tank. So the hydrogen tank will only be charged when the excess of the PV generation is high, which results in that the price is low. So the electrolysis is primarily driven by the PV circuits, which in turn coincident with the low price in the hour. So the hydrogen will be utilized when the price is low, especially in the summer. And we compare the cost saving of each household, we see that we can reach a maximum of 60% saving in the battery degradation and have 45% electricity cost per annum. So with one household, we can reach 45% reduction in the annual electricity bill. So we see that despite all this low long-term efficiency of hydrogen, the hydrogen storage system still shows potential in lowering annual electricity costs of the household. So let's talk about the conclusion. So we see that households could use the hydrogen tank to reduce the electricity cost and battery cycles. And from the side of grid operator, it can use hydrogen tank to reduce the grid peak load and also the annual total feeding. It also provides a flexibility for the whole energy system. So if each microgrid is equipped with one hydrogen storage, so we don't have the problem of the megagrid. We see that the shared hydrogen storage creates value at all the household, grid, and the system level. But there is also some limitations, so we do this based on the historical data within a one-year scenario. And in the coming step, we will analyze the economic feasibility. So we want to transfer these numbers into economic feasibility and analyze whether it is meaningful to invest in such hydrogen system in one microgrid. Yeah, thank you for your attention. If you have any questions,
thank you very much for your excellent presentation. Would anyone have a question for the presentation?
Thank you very much for the talk. And just a quick question about the social acceptance of hydrogen. When you talk about hydrogen and mostly the household, you really need to think about, are people really ready to use that? Have you thought for that side of this project?
so for the social acceptance, so we maybe we could discuss also the safety, like if we introduce the hydrogen into a microgrid. But in this case, if the household, so if we prove that one household it is connected to the external hydrogen storage and it can reduce the electricity bill, I think most of the households wants kind of some second storage option because the annual, like the electricity bill, could be reduced. But from the microgrid side, we must also consider about the safety or the noise that the hydrogen storage system could produce. If we build one hydrogen storage system for each street, so on every street, then it will maybe cause some safety-related problems.
And do you know what's the pressure of hydrogen storage tanks for this?
Yeah.
What's that?
I think so. Because of the hydrogen tank, so when we talk about the cost of a tank, the cost of a tank increase not linearly actually. So it's also our next step to investigate the economic feasibility. So we want the household to also put some investment into the system, and the grid operator also see some benefit, make investment, maybe also the government, when with such second storage system could make the energy system more flexible, then the government maybe also
there are not questions?
Excuse me, just one question. You speak about the grid operation. How you manage the supply and demand? Because I'm speaking about the grid operation, I need the management of the energy storage system. For example, using the energy. There is a difference between the peak demands, for example, during the peaking hours and during the other hours. So what's the topology that you apply for management between the supply and demand, especially in the peak hours and the contrast with other hours that there's no peak demands?
Yes, because we use the historical data, so the peak, so the big demand like in the winter because everyone need to eat their houses, and also the peak generation in the summer, so they are all included like in the historical data. So that's the case that we use the historical data because we want to replicate the need of a second storage system. We want to analyze whether there is an actual necessity of having such system. Because the peak and tile will be included in the historical data.
Yeah, thanks so much. But another thing that you can consider that you are buying the cost, for example, if the cost during the peak hours will be reduced, it will be good for the customers to apply for other hours instead of using the peak hours. This will give the management of the supply. Sometimes it's not about the grid provider, it's about the customers that are supplying.
Yeah.
Thank you so much.
Yeah, thank you for your question.
Okay, thank you once again for your presentation. No question? Okay, thank you once again for the presentation. It is you move to our second presentation. C'est my presentation. Traveria, Morocco, from Laboratoire of Physics, Energy, Environment and their application. In this presentation, I will talk about optimizing distribution, network configuration, and renewable energy integration for power loss reduction. The plan of my presentation, first the context and objective, second the system and scenario, third the result and the discussion, and finally the conclusion. Let's talk about radial distribution network or RDA on the most fundamental and widely used structure and power distribution system. A radial distribution network has a tree-like power system structure widely adopted for medium and low voltage electricity distribution, power flow and single direction from distribution to the right of a simple topology and low implementation cost. With objective minimiser total active power loss, enhance overall system performance and stability, improve voltage profile across the network. Methodological approach are 1. Developed and applied a hybrid binary particle swarm optimization PPCO and Greenholt optimization GWO optimization algorithm. Integrate renewable energy source solar PV into the distribution system. Confirm that network radiality and operational constraints are respected. This system to standard New York system are frontally bus and 69 bus and introduced by Baran and we, the common realistic in your fight, chosen so anion can combine will result directly with the literature. This system and scenario, I have 3 scenarios. One scenario was standard radial network configuration, non-distribution generated integrated with as reference for loss, voltage and stability performance. Scenario 2 with DG only, renewable base DG solar PV are integrated into selection bus. Network topologie romain and changé non reconfiguration. L'objectif observe impact of DG L1 on power loss and voltage profile. Scenario 3, the DG allocation after reconfiguration. Network is forced reconfiguration to optimal topology using the hybrid PPCO et GWO algorithm. The DG init are optimally allocated based on the new configuration. L'objectif combine the benefit of topology optimization and l'intégration DG for maximum performance improvement. We received a discussion for 3333 EE derived from barn and with original configuration consists of 23 bus and 32 distribution branch. Include 5 seat switch normally open and 32 selection switch normally closed. Used for validity of configuration algorithm and realistic manageable condition. Scenario 1, base cars. Identical scenario base case, powerless result obtained with GWO unit PPCO and hybrid PPCO GWO on EE33 test system for this configuration. Identical result across all 3 method device serve as reliable reference before DG integration and configuration. Scenario 2, DG only. Despite different DG placement and 3 algorithms converge to decide power loss level for all 3. Showing that DG integration alone are robust and consistent improvement over the base case. Work determination power loss, reactive power loss, voltage deviation, voltage stability et DG bus. Des résultats PPCO archive the lowest power loss et will install for this total DG capacité in GWO et PPCO, confirming that configuration of what optimization DC allocation delivery both later performance and a more cost-effective solution. Show the final configuration of EE33 is sectionalism switch switch désintégration point of the solar energy source 3. Powerless foresee optimization algorithm evaluated on device pins, DG only and DG after all configuration scenario. Is 459 kilowatt. Base case loss identical for an algorithm non-DG, non-configuration, adding DG along peak list by 65 to 71 kilowatt. Reconfiguration and DG with loss further going to 14.9. PPCO conclusion. PPCO GWO proposed method give the best result on scenario 3. Derived from parent and original configuration of 69 bit radial distribution system consist of 69 bits and 60 distribution branch, include 5 cities which normally open and 68 selections which normally closed. Used for validating reconfiguration algorithm and realistic youth management condition. The result and discussion of this system 69 identical results across all 3 methods divised car serve as reliable reference before DG integration and reconfiguration. Scenario 2, DG only. Despite different DG placements, all 3 algorithms converge to the same power loss level, showing that the DG integration alone already lead a robust and consistent improvement over the base case. Scenario 3, DG allocation after reconfiguration, power loss result obtained with the 3 algorithms for EBIS 69 distribution system. PPCO GWO achieved the lowest power loss 32 when installing the last total DG capacity among the 3 algorithms, confirming that combining reconfiguration with optimized DG allocation delivery both better performance and a more cost-effective solution on the 69 as well. Some India bigger neutron, where is the final solution hybrid PPCOG font. Here is the systematic of distribution network bus after applying the optimization algorithm. Again, you read the shade line, and the switch is open to reshape the network. The 3 solar unity is at bus as 3. The exact configuration is what produced this is as produced this 22 lowest power. Donc, base phase identique for all algorithms non-DG, non-reconfiguration. Adding DG alone plus cost by 69 to 62 reconfiguration and DG to loss further. En conclusion, a hybrid your proposed a hybrid PPCO approach your proposed to join optimiser network configuration and renewable DG allocation, reducing power loss forum, a total reduction of 76 on the 23 piece system and 86 on the 69 bus system. This diagram form with improved voltage stability, a significantly lower installed DG capacity, and solution that is both more effective and more cost efficient. Thank you. Thank you for
Thank you so much, Bursa, for this presentation. I believe the distribution system is very important, especially in power system and especially, for example, in supply fields, because I come from Portugal and the Libya, so we face this problem. As you mentioned, for IEEE 33 bus distribution, you have present different level for 3 level, and my question is, how we can minimize the power distribution IEEE bus in order to regarding the voltage profile, because as you mentioned, sometimes you minimize the voltage distribution system, but you need also to consider the voltage profile in order to allow the grid to operate with a certain operation concentrate. Another thing, as we know, the power loss comes from the high lines, the bus feeder distribution for the high lines when we have longer distance, because this comes from due to the resistance of the wires. Do you think that it's effective to use the algorithm or another way that we need to break the wires and use another transformer to increase the power? Because this is one of the solutions. Thank you so much. You mean that you come with optimization techniques?
Yes.
Okay.
For having a lot of combination of this grid.
Yeah, I know that one of the configuration that you apply different optimization techniques for the configuration of the microgrid. But when you apply this one for using the active power, then you consider the active power, because the grid will not have a limit of the operation. It means that you have just work with active power.
Yeah.
Thank you so much.
Thank you. No question? Question?
No, you can speak a lot.
Like in French. She finds
Yeah, that's very good.
Thank you.
It's very advanced.
Yeah.
No. Question. No. New question. Thank you.
belonging to the Spanish Ministry of Defense, and I wanted to talk about the energy management to promote an active participation of small and medium prosumers in renewable energy systems, and how we experimental validated using a distributed multi-agent architecture. So nowadays, all we already know that traditionally the energy was produced by really few companies that and sell this energy to the consumers that take this energy to do great things. But this scenario at the moment is totally different. There are many agents that can both produce and consume this energy. So if we don't do a good management of this energy, we will be in trouble, as we suffered in Portugal and Spain and many other regions in April on 2025, that we suffered a blackout. So we have several hours without electricity and many problems during this period. So today I wanted to talk about what is the demand side flexibility and how it is becoming even increasingly essential in power systems with high renewable energy penetration, and how energy management system can coordinate this generation, this storage, and the consumption of this energy. So then we will talk about experimental validation, about this philosophy and this several facilities during the ECRES project. This project is co-funded by ONPONS and interregional cross-border cooperation program from the European Union, is coming from the Portugal and Spanish borders. So, as all we know already, traditionally the energy, the grid control, were so simple. The producers have to adapt its production, energy production, to the demand. All the produced energy must be consumed by the consumers. If it is not balanced, there are more production than demand, or demand more than production, the system will go down. So we have to adapt, or we have to learn where or when do this consumption in order to make this system balanced. So the consumer now can play several roles. The role that they can play are the traditional consumer that only consume this energy. It can change or move to a prosumer that both produce and consume this energy, or be a flexible consumer that this kind of consumer can shift this consumption or not critical consumptions to time or to periods that there are more availability of energy. So the demand side flexibility is not about to do a better consumption. Better consumption understood as better efficiency. For lower consumption, but to have the ability to adapt this consumption or this generation to the power availability or any of the power systems. So this is not possible without an energy management system. This energy management system can be a facility or a device or something like that to make a decision in order to optimize some aspects of the facility. They take the production data, the battery state, the energy consumption of the users, forecast weather forecast, and the market price in order to make a decision to optimize some aspect of the facilities. So depending on the strategy followed by the EMS, we can reach one optimization level or another. We can deploy a very simple, rule-based, for example, strategy, or increase the complexity of this strategy, adding some predictive optimization, predictive controller, artificial intelligence, and so on. These mechanisms are used in the optimization of this management. So the consumers or the agents now stop being isolated isolated consumers or isolated agents. Sorry. But they take part from an energy community or even taking part as each facility has its own capacity or own capability, they can take part of an electricity flexibility market. So they can cover some necessities or some needs of the power system, even if they are consuming or they are producing, and the system needs some consumption or some production. So until now, this is a theoretical concept, but we wanted to learn these concepts into a real world conditions. So we take energy storage and try to manage this energy following some strategies. So and using a multi-agent architecture. So the battery, we are producing a battery. The battery, the system have to decide when to charge, when to discharge, when to stay idle, depending on the available information, depending the generation, the demand, the state of charge, the price of the energy, and so on. So the architecture that we followed was, as I want to explain now, the University of Algarve, that is, all of these are partners of INTA in this project, and we take this partnership. So University of Algarve took the generation and the demand data from the Pulatra Island, that is an island located in the south of the peninsula, the Iberian Peninsula, in Portugal, really close to Faro, and is an energetic community that has implemented some generation through solar panels, and they are a really small town that can many neighbors are subscribed to this project in order to give us the consumption data. So the University of Algarve centralized this data and sent us to the IoT platform developed by the Technological Institute of Galicia. This is located on servers in the north of Spain, in Galicia. So the University of Seville, Seville is in the south of Spain. So they take this data and runs an optimization algorithm to obtain some set points for the batteries. INTA, my organization, takes these set points from the platform and apply it to a real-world battery, a battery bank that is in Huelva, in the south of Spain, and produce, make it work. They put the set points and control the state of the batteries. And then this data is taken back to the platform in order to validate the algorithm and to balance the generation